Hello students, welcome back to the course on Principles and Chemical Applications of Thermodynamics. We will continue our discussion on the applications of thermodynamic potentials in real systems. And here I would like to mention that this would be a continuation of our discussion on how to use thermodynamic potentials to understand the behavior in isolated and non-isolated systems. We have already seen that in such systems, the condition of spontaneity and equilibrium are given by certain thermodynamic potentials, which are nothing but energy functions. And for different experimental situations, whether I have an isolated system or system in thermal contact with a thermostat or a barostat or both of them, I can define the condition of spontaneous change in state and the condition of equilibrium by saying that in each case, a change in state will occur in the direction where there is a decrease in the corresponding thermodynamic potential. And when will the final equilibrium state be reached? The final equilibrium state will be reached when, under the given condition, the thermodynamic potential is minimized. So now we understand the importance of thermodynamic potentials while we understand the behavior of a given real system. Now we have also introduced to you the Maxwell's relations, whereby we have used the property of thermodynamic potentials and as exact state functions. And in relation to this, we have introduced to you a set of 4 equations which we call the fundamental equations of thermodynamics. And by exploiting the exact nature of the differential of each of these thermodynamic potentials, we have been able to get a set of 4 relations called Maxwell's relations. For the practical application of thermodynamic potentials in real systems, we have said that we are going to use these Maxwell's relations. Of course, for a student looking at these Maxwell's relations for the first time, it's very difficult to remember which of the partial derivatives equate which ones. So for this, I have taught you this very simple mnemonic, sportive, and I have shown you how to derive the Maxwell's relations just by looking at this picture where SPTV reminds you of this particular word, sportive. Now the question is, how am I going to use these Maxwell's relations to solve some of the problems at hand? Let us first look at how to find out the internal pressure pi t. Now, do you remember how I defined pi t? Pi t is the partial derivative of the internal energy U with respect to volume V under isothermal conditions. So given this definition, we can now have a look at one of these fundamental equations of thermodynamics and look at how to use the Maxwell's relation to obtain an expression of pi t in terms of measurable properties of the system, irrespective of whether the system is an ideal gas or a real gas or a liquid or a solid. So the discussion that I'm going to put forward here is going to be perfectly general in nature. So let us start from this fundamental equation du is equal to TdS minus PdV. Now, what is the quantity that I am interested in? I am interested in understanding the variation of U with respect to V under constant temperature condition. I can determine this quantity by taking a partial derivative with respect to V on both sides of this equation. So that is exactly what I will do in the next step. So what do I have now on the left hand side of my equation? I have del U del V T, and now under constant temperature condition, the right hand side is given by T into del S del V T minus P. Now, can I use this particular relationship directly for a given system and find out what del S del V T is? And then if I know the temperature at which the system is present and the pressure, I should be able to find out the internal pressure. But as I have already mentioned to you, it's not very easy to find out S as a function of V for any given system. And therefore, I need to convert this particular quantity into something that is more easily measured. And for this purpose, I'm going to use the Maxwell's relations. Now, what do the Maxwell's relation tell you? It tells you that del S del V T is equal to del P del T V. So, while writing this down, all I'll have to do is write down sportive again, S, P, T and V. So, what do I need? Del S, del V, T. Then what would be equal to? It would be equal to del P, del T, V. Now, as the first step that I'm taking in finding out these partial derivatives is vertical, and therefore I don't have to add that negative sign. And therefore, even without consulting the list of Maxwell's relation, I can very quickly say that, well, this particular quantity that can be replaced by a much more useful quantity, which is del P del T V. So, if I now write down the expression of del U del V T, this now turns out to be T into del P del T V using Maxwell's relation minus P as before. Now, we have used this relationship before. We have seen this relationship before. Where did I see it? I actually gave you to work out this particular relationship starting from the relation that if P can be expressed as a function of T and V, then you can use the cyclic rule for the partial derivatives and show that del P del T V is nothing but alpha by kappa. Now, what is alpha? Alpha is the isobaric expansion coefficient, and by definition, this is 1 by V del TP. So, as you understand, if you subject your system to a variation of temperature under isobaric condition, the resultant fractional change in volume will give you the alpha. So, alpha can be measured in an experiment involving pressure, volume and temperature, all of which are easily controlled and measured when you are performing this experiment in the laboratory. Now, what is kappa? So, let me remind you that kappa is nothing but the isothermal compressibility, and by definition, this is the quantity that you measure when you have kept the temperature constant, you are varying pressure, and you are looking at the fractional change in volume, and you measure the fractional decrease in volume with increasing pressure. So once again, both the quantities are outcomes of measurement of pressure, temperature, and volume in the laboratory, and this can be easily done. So once I know this, then what I can do is I can actually simplify my expression and do the following. I can now say that pi T, that is my internal pressure, this is now given by alpha T minus kappa minus P. So in this case, as you see, I can, if I know and if I can measure the properties alpha and kappa for a system, if I know the temperature and pressure at which I am interested to know the property of the system, I can find out what pi T is. You would remember that pi T is also related to two more quantities, mu J, that is the Joule coefficient, and Cv, that is another measurable property of the system. And therefore, if you, for some application, if you're interested in knowing what would be the Joule's coefficient for this system, then all you will have to do is look back at the property chart and say, well, do I know the specific heat at constant volume of this system? Do I know the alpha and kappa of the system? Then, if the system is present at a given temperature and pressure, I can very easily find out what the Joule's coefficient of this system is. So now you see what we have achieved. We wanted to find out one quantity which was not really accessible to us directly from the first law of thermodynamics. Now, using Maxwell's relation, we find that I can measure pi T or equivalently mu J in terms of measurable properties of the system such as Cv, alpha and kappa for a given equilibrium state of the system. Let us next go to a second application, and in this case I am going to estimate Cp minus Cv. Now let me remind you the definitions. So what is Cp? Cp is the partial differential as shown here. So if I am heating a system under isobaric condition, then the rate at which the enthalpy of the system changes with respect to temperature defines Cp. Similarly, Cv corresponds to the rate of change of internal energy when the system is heated under isochoric conditions. Now let me try and derive an expression of Cp minus Cv, not just for an ideal gas, but for any system in general. So for this purpose, I will start from the definition of enthalpy. So let me remind you, what is the definition of enthalpy? That is internal energy plus PV. What is the quantity that I am interested in knowing about enthalpy? That is del H del T P. So I will take a derivative with respect to T under isobaric condition on both sides of this equation. Therefore, I can write Cp is equal to del U del Tp, That is a term which I have obtained by taking a partial derivative of u at constant pressure, and then another term, that is plus p into del v del Tp. Now, where did this term come from? When I take a partial derivative of this term with respect to temperature, keeping pressure constant, pressure comes out of the derivative, and this is what I am left with. Now, I can do a further simplification of this expression. So, here I note that the isobaric expansion coefficient can be used for the term here, which involves del V del Tp, and del V del Tp is nothing but alpha into V, and therefore I can write Cp that must be equal to del U del Tp plus P into alpha V. Once again, therefore, what I will do is I am going to put in this expression for Cp in the expression for Cp minus Cv. Now, Cp minus Cv is equal to, then this is the expression for Cp that we have derived, minus Cv. Now, I will take over from this expression where I understand for a given state of the system defined by P and V, if I know alpha, if I know Cv, I know the two terms present in this equation. So, the next task would be to express this particular term del U del Tp in terms of measurable properties of the system. So, that is where we start from in this part of the discussion. So, I have Cp minus Cv that is equal to this term plus P into alpha V. Now, I will once again use the fundamental equation of thermodynamics. And now I have written du is equal to Cv dt plus pi t dV, where Cv is the specific heat at constant volume of the system and pi t dV is the internal pressure. Now, from using this expression, I can always write down what is del U del Tp. So, all that I will have to do is take a derivative on both sides of this equation with respect to temperature, keeping pressure constant. And when I do this, this is the expression that I will get. Once again, I say that look, there is one place where I can replace the partial derivative using the definition of alpha, a measurable property of the system. And therefore, I can say that del U del Tp minus Cv, I have taken this Cv on the other side of the equation. So, del U del Tp minus Cv turns out to be pi t into alpha into V. In order to find out Cp minus Cv, I needed to find out del U del Tp minus Cv, right? And that is equal to pi t into alpha V. Therefore, I can very easily say that what is pi t here? We have already shown that pi t is related not only to alpha, but also to another measurable property kappa if I know at which temperature and pressure the system is present. And therefore, what I am going to do is, I am going to write down Cp minus Cv using first these two equations. That gives me the right hand side as alpha into V plus into pi t plus P. Now, what is pi t plus P? If I use the definition of pi t plus P is nothing but alpha t by kappa. So all I'm going to do is, I'm going to take this value and put it back here. If I do that, then the final expression that I get for Cp minus Cv, that is alpha square T into V divided by kappa. Now, if you want to find out the value of Cp minus Cv for any given system, in that case, as you can very easily see here, what are the quantities that you need to know? You need to find out the thermodynamic state at which the system is, which will tell you about the volume of the system and the temperature of the system. You will need to know the isobaric expansion coefficient alpha of the system and the isothermal compressibility kappa of that system. And once you know all these quantities, irrespective of what type of system you have, you will be able to estimate Cp minus Cv for that system. Now, let us go and have a look at one more application of the Maxwell's relations. Here, I am talking about determination of the value of the Joule-Thomson coefficient. It may so happen, of course, we have already discussed that mu Jt is something that you can measure in a Joule-Thomson experiment. My question is, given the thermodynamic state of the system, is it possible for me to predict what is going to be mu Jt in terms of other known response functions of the system which have been widely determined and tabulated in the literature? And for this purpose, I am going to use this definition of mu Jt, which we have already discussed in my earlier lecture on enthalpy. Now, here again, I am going to start from another form of the fundamental equation of thermodynamics. And what is it that I have here? I have dH equal to TdS plus VdP. Why is it so that I am starting from this equation? That is simply because in order to find out mu Jt, I need to find out del H del Pt. And this is the perfect starting place to determine this partial derivative because it gives me dH. So if I now take a partial derivative with respect to P on both sides of this equation, keeping temperature constant, what do I get? I will get del H del Pt is equal to T into the partial derivative of this term. So that is del S del P T plus V. Once again, the task is replacing the partial derivative involving the entropy. How are we going to do that? We will do that using the Maxwell's relation. Now, which Maxwell's relation is going to be useful here? So, let us once again write down the sportive S, P, T, V. So, what do I need? I need del S, del P, T. What is it going to be equal to? It is going to be equal to, so what is the what is the symbol that I did not cover while going from S to here, del S, del Pt. So, this is the symbol that I did not cover while starting from, while evaluating del S, del Pt. Therefore, this must be equal to del V, del Tp. Now, as you see that the partial derivative, in order to equate the partial derivative, My first step is a horizontal one, and therefore I would have to write down a negative sign here. So as you see, what I have is del S del P T, that is equal to minus of del V del T P. Now, does the introduction of Maxwell's relation here help us? The answer is yes. That is because using this, now I can write down del H del Pt is equal to T into del V del Tp plus V. And this particular relationship is familiar. That is because that is nothing but alpha into V, where alpha is the isobaric expansion coefficient. And therefore, if I put it back, now I have a relation which says that del H del Pt can be determined if I know what the alpha of the system is, if I know the volume and temperature at which the system is present. Now, using this relationship, I can now put it back in the definition of mu Jt, and this is the resultant expression of mu Jt. So mu Jt is now given by V by Cp into alpha T minus 1. Now let us say that you have this task of finding out if you are going to, for some practical application, you are going to pass one given gas from a region of high pressure to low pressure. The properties of that gas is quite well known, and you would like to know whether this gas is going to expand or it's going to heat up or cool down on such expansion. All you will have to do is look at the temperature and the volume that the gas is maintaining, look at the value of alpha and Cp under the given conditions, and then you can immediately find out whether mu Jt is positive or negative under that condition. And you can immediately say, well, since I'm going to use this gas, it will cool down on going from this high temperature region to the low temperature region, or the other way around. So this is exactly how the Maxwell's relations have been used in practical applications. So to conclude, what I would like to highlight over here is as follows. For a system at equilibrium, we can always say that du equal to TdS minus PdV, and then take a derivative, and then you typically arrive at a relationship like this. Or you can rewrite the fundamental equation like this for H, so that all the quantities which appear on the left hand side, they involve they involve pressure, temperature and volume as the experimental quantities, which can be controlled in the laboratory environment very easily. And therefore, the utility of Maxwell's equations has been summarized here. As you see, we started from the fundamental equations where the S was involved in each case. You know that I need to understand du, dh, df and dg for a given change in state, and I find that they are dependent on the measurement of entropy, either its change or its absolute value for a given state, to be able to predict whether this particular system will undergo a change in state spontaneously. And now you have these equations where you see that each of these conditions now, each of these quantities now have been expressed in terms of measurable properties of the system. So that is why the Maxwell's relations occupy such an important position in the literature of thermodynamics. So we would conclude that if you want to apply the thermodynamic principles in real systems, you have to use Maxwell's relations. Thank you.